So it's time to start. Today we'll switch topics. We'll be discussing, today and next time we'll be discussing elements of graph theory. Graph theory is also a very important and well-developed area of combinatorics. Graphs show up in many applications, starting from, I don't know, road design, to chemistry maybe, and many other places. Usually in practical applications, quite elementary things about graph theory are important, but in general, mathematicians do not care about applied stuff mostly, and they want to solve difficult problems which they find interesting. Sometimes it's a good idea, sometimes it's a stupid idea. Because usually you want to have something which have meaning in real life as well. Okay, so let me maybe share my screen and we'll start discussing graphs. Classically, one attributes the beginning of graph theory to the same person as you may seen in calculus courses, namely Leonhard Euler. So he was apparently the most prolific mathematician of all times. I don't know, he's collected papers, maybe it's about 50 volumes or more than that. He mainly worked in analysis, and but he also made a small contribution to what is considered to be the beginning of graph theory. So we're talking about middle of 17th century. And for some period of time, he was living in a German town of Königsberg, which is now belongs to Russia. And they had a small river, Insel maybe, I don't quite remember how it was called. Okay, so locally the situation was as follows. So there was small islands inside the river. So this is the river. And also, so this is the mainland. So the islands were connected. Maybe I remove those things. So the islands were connected to each other and to the mainland by 7 bridges. So the picture I found in the literature looks like this. So there were 1, 2 bridges, another 2 going like this, and then there was a bridge in between to the 2 islands, and then there were 2 more from here to there. And for some reason, so rich people who didn't have much to do were asking, so whether it's possible, question which Euler finally answered, is it possible to start somewhere, to start at a point, then go over all 7 bridges exactly once over each and come back. So you can kind of remove everything which has with landscape to do, and you can just think that you have a picture like this. And so you use your abstract thinking and you want to understand whether it's possible to, so all these ends you should probably connect. So you should connect these three ends to one, because this is, the mainland on one side. Should be a situation like this. And the three going to the other side, you can also connect to one point. And you have a picture like this, and you are interested in, if I start somewhere, say here, for example, can I go over my edges, which are representing those bridges, covering all the edges, covering all the bridges, and using each edge once and coming back. And so Euler developed a nice theory of so-called Euler's graphs. I don't think he ever used the term graph, which we're using now. And he characterized completely such abstract pictures consisting of nodes and links between them, which are nowadays called edges, and nodes are usually called vertices, such that such a picture with nodes and edges, with the vertices and edges, allow you to start at some vertex, go around this picture, covering each edge once and coming back. So we'll probably discuss this more next time. So this was one very, very old question, and his result can be maybe considered as the starting point of what then developed into graph theory. Another question was also an old question, definitely from the 18th century. It was kind of children's problem for children. Say if you have another example, nice example. Maybe you have seen it when you were children. So given three houses and three wells, can you draw a road from each house to each well so that they do not cross? Okay, what do I mean by this? Say here we have three houses, and we draw them in the plane. Now I have three wells here, and I want to draw a road or a path in the plane connecting each house to each well, and say neighbors don't like each other, so they don't want to meet. So I want my roads not to cross each other. Okay, so if we start doing this, say it's easy to connect one house to all three wells. It's not difficult to connect the second house to all three wells. So then we can connect the third house to two of the wells, but to connect it to the third well seems to be difficult. And it took quite a long time to actually prove that this is impossible. So in this question, in modern kind of terms, or maybe terms which were developed maybe some 70 years ago, this was about planarity of a certain graph. Can a certain graph be embedded in the plane with its edges non-intersecting? This is the second motivating example. Now let's start doing formal definitions and some basic properties. So, okay, so basic definitions. Okay, a graph is a collection of vertices, of nodes called vertices, and edges, which are, in other words, pairs of vertices. So, and this is it. I want to mention that, so there are certain versions of this, versions. So edges can be directed or non-directed or undirected. So edges can be multiple or simple. I'll explain what this is. And finally, edges can be loops. So there are different classes of graphs depending. Okay, so let me draw some naive example. Say we have a bunch of vertices, nodes. I'll draw them on the plane, but you don't have to always think that they sit in the plane. This is an abstract gadget. So when we have, say, a bunch of edges like this, so this is, say, an undirected graph with a loop. So I don't have directions. There is no, so you can think of this as roads, so which are, you can travel both ways, both from one to the other and back. And I might allow edges or not. So, so this, so I'm sorry, I might allow loops or not. And I might allow, say, several edges going, connecting two vertices, the same vertices, multiple edges. So it depends. So in many situations you have to specify which kind of graph you want to talk about, and many of these different versions of graphs have meaning and have sense. So for example, this is a directed graph with a loop. So this is an undirected with loops and multiple edges. So this is directed graph. So typically, so notation, basic notation is usually, so G stands for a graph, and then usually you say it consists of two sets, V, which is the set of vertices. So V is the set of vertices. And this is the set of edges. And okay, so we need to, first of all, to find some natural equivalence relation between graphs, because we can draw our pictures here and there, but we actually were only interested in the interrelation between vertices and edges. So we need to be able to identify graphs. So the basic definition is two graphs, G1, which consists of the vertex set V1 and E1, and G2, which consists of vertex set V2, E2, are called isomorphic. If there exists one-to-one bijection between vertices, say B sending V1 to V2, which induces a bijection of the edges. So there is a way to identify vertices of one graph and the other graph so that edges will be mapped to edges under this correspondence. Okay, so yeah, I also forgot to mention, so okay, so let us draw some simple example. Say we want to classify simple unoriented graphs on, say, 4 vertices. Simple means there are no multiple edges allowed and no loops. And unoriented are unoriented, so edges do not have any preferred direction. Preferred directions usually are important in some economical or maybe traffic applications where, you know, direction is, if there are some directed roads which you can travel only one way, so then it's natural to use directed edges to model those things. Okay, so draw all non-isomorphic simple graphs, say with 4 vertices. Okay, so let's try to do this. So we have our vertices. So this would be 4 vertices, no edges at all. This is the very basic trivial graph. So the second graph, say we have 1 edge. So there is only one up to isomorphism simple graph on 4 vertices with 1 edges. So what about 2 edges? 2 edges can be like this. Yes. But also 2 edges can be like this. So these are, so no edges, 1 edge. So here we have 2 edges. Okay, now we have to think about 3 edges. Yes, 3 edges can be a situation like this, a triangle and a separate vertex. Then it can be a situation like this. And nothing else, I guess, 3 edges. Now what about 4 edges? 4 edges can be a square, yes, and 4 edges can be a situation like this. So this is 3 edges, 4 edges. Now 5 edges.
Shouldn't 3 edges, shouldn't one be able to connect to 3 nodes, 3 vertices?
Are you?
If you call the top left one V1, and then couldn't that connect to the other 3 vertices for 3 edges?
Yeah, thank you. Yes. So there, I'm missing here the guy. Yes, I agree. So there is a guy like this. Yes. Yeah. One edge connected, one vertex connected.
Yes,
yeah,
exactly.
Yes. Good. Now 4 edges, what do we have? So 4 edges, we had this and that. And I guess this is it with 4 edges, yes? Yeah. Now 5 edges, what do we get there? So 5 edges, we can have a square with a diagonal. Yes. And what about this guy? And then I want to connect this to here. Yes, like, oops. Come on, like this. So this is a different person. And let's see. I think this is it, yes. And now finally, there is just one. So this is 5 edges, and this is 6 edges. Finally, there is one graph which is called complete, where we're putting in the maximal number of edges, which is 6. Now let me make a small observation or maybe question to you. So how many edges can a simple graph, a simple undirected graph on n vertices have? So what is the maximal number of edges we can put in if we do not allow multiple edges and we do not allow loops? So Titi, you should probably know.
I probably should, but since I took combinatorics this spring as well, but I can't remember actually.
Well,
but it looks like for this example, it's kind of 4 correlates with 6 in so many ways. So I can't really say which one it is.
Okay. Let's start. So let's start if we can guess this. So if we have 2 vertices, there is just one graph. Yes, but there is just one edge. I mean. So for n equals 2, we have 1. For n equals 3, how many edges can we get? The maximal number should be 3, yes? This is a triangle. So for this guy, we get 6. Now, what about the next guy? So I'm drawing all of them. How many do I have in my picture? So this is 10.
10.
So 1, 3,
so
6.
It's binomial coefficients.
So which one? So the answer is
n/2.
Yes, n choose 2, of course. Because why? Because what is an edge? An edge is a pair of vertices. So how many ways there are to choose pair of vertices when we have n vertices? N choose 2. Okay. Yeah. So so a basic question. So this basic question of how many non-isomorphic graphs are there with n distinct vertices, it does not have a good answer, for example. So remark, a basic question about the number of non-isomorphic graphs with n vertices has a bad answer. Meaning, well, there is no nice formula for that. I mean, so definitely computers know this number up to horrible large number of vertices, but there is no nice formula for that. So typically, so let me also add some more definition. So a graph is called vertex labeled if its vertices have individual names. So we're not allowed kind of, yeah, so we're distinguishing. So typically, I mean, such situation occur in practice. Say, if we have a traffic net, a road map, so we know that each node, say, is a city. We cannot switch around cities. Each city has an individual map, an individual name. We cannot switch them around. And edge labeled, the graph is called edge labeled if its edges have individual names. So typically counting questions, so say if we want to count the number of graphs with such and such properties, experience shows that it's much easier to find good counting formulas for labeled, maybe vertex labeled or edge labeled. The graph can have both vertices and edges labeled. So labeled graphs are typically much easier to count than if we allow all possible isomorphisms, so to say, of graphs, because a graph can have a lot of inner isomorphism. Sometimes you can switch the order vertices around, relabel vertices, and get up to an isomorphism, the same graph. And this circumstance makes counting problems usually quite complicated. Okay, so what is it that I wanted to tell now? So, yeah, so a path, so a path is a sequence of vertices non-repeating maybe vertices, each two consecutive connected by an edge. So it's a very naive, simple notion. Say if we have a graph, something like this. So a path in this graph is, say, for example, we start here, we go from this vertex to that vertex, and then say we go from that vertex to another vertex, and then say we go up to that vertex, and then we go down. So this would be a path in our graph. And the path is called a loop if we start at some vertex and come back to the same vertex. We make a closed travel inside our graph. Okay, now maybe it's a question. So how to describe or present graphs? So there are two natural matrices. There are many more, of course, but there are two very basic matrices associated to a given graph. One is called the adjacency matrix, and the other is called the incidence matrix. So two basic ways and many more others. So I'll be talking about the adjacency matrix. This is number one. And the other one is called the incidence matrix.
Just a short question. In a path, can vertices be repeated?
It depends. So there I mean, so what we usually require that edges should not be repeated. But sometimes we allow vertices to repeat, sometimes not. So it's usually specified in a problem. What we definitely don't want to allow is repeating of edges. So we don't want to go back. Okay, so what is an adjacency matrix? So the adjacency matrix of a given graph maybe usually is denoted maybe A of G is a symmetric matrix which has both rows and columns labeled by vertices in some order, and the entry in this matrix is if a vertex vi is connected to a vertex vj, so say I and j here, so they will be typically putting a 1 in this position, so 1 in position ij means that the vertex vi is connected to vj. So such a thing allows us also to incorporate to find adjacency matrices for both undirected and directed graphs, of course. Yes, if our graph is undirected, so this matrix would be symmetric. Yes, because I is connected to j if and only if j is connected to I. It allows us also to maybe encode multiple edges. If I is connected to j by 3 edges, we can put the number 3 there instead of number 1. It also allows to incorporate loops. For example, if you have a loop connecting vi to itself, or maybe several loops, you just put on the diagonal the number of loops connecting vi to itself. So it's a nice flexible notion. Okay, if your graph...
Sorry, can I just ask, could you,
Yeah,
is it always from I to J? I mean, is it rows to matrix, to columns?
Well,
or is it, I mean, is that matrix, is it directed in any way? Or could you just as well say that it's J to I?
To write a matrix, you have to order your vertices. You have to order, say, this is number 1, this is number 2, this is number 3. I'll do an example, maybe it will explain.
Thanks.
Okay, so say we have such a graph, for example. Well, if we don't have labeling of vertices, we cannot create a matrix. But the labeling of vertices is not so important here. If we label them in a different way, we'll get a matrix which is similar to other labeling. There is an exact equivalence relation between matrices which are obtained from a given graph under different relabelings of vertices. But to create a matrix, we need to fix some order of our vertices. Say I'm saying this is V1, this is V2, this is V3, this is V4. Okay, then we're getting a 4x4 matrix. So V1, V1, V2. Okay, so V1, V2, V3, V4, V1, V2, V3, V4. So we're fixing the ordering of vertices, and this fixes the ordering of both rows and columns. Okay, let me maybe add a loop here. Just okay, so V1 has no loop, so we're putting 0 here. So V1 is connected to V3, and V1 is connected to V4, and here in the first column we're putting the same thing because V3 is connected to V1, V4 is connected to V1. Okay, now what about V2? V2 is connected to itself. We're putting a 1 on the diagonal here, and V2 is connected to V3, and V3 is connected to V2, like this. Okay, V3 is connected to V1, this we have already, to V2, this we have already. It has no loop, so we're putting 0, and it's connected to V4. And so this is our matrix. V4 has no loops, so there is a 0 on the diagonal. Okay, so if we had, say, multiple edges, say if I want to do some a little bit different example, say we have a directed graph maybe, and with multiple edges, I don't know, something like this. Yeah, like this maybe. Say again, say let us take V1, V2, V3, V4, just for simplicity. So those edges which are not directed, meaning that they are directed both ways. We can always think like this. So V1 has no loops, 0 here. So V1, V2, V3, V4, V1, V2, V3, V4. Okay, so this column will express, so V1 is connected to V2, and V2 is connected to V1. We have ones both ways. Now V1 is connected to V3. We're putting 1 here, but not the other way around. So this would be 0 here. Now V1 is connected to V4 twice. 2 edges, 2 edges. Now V2 is connected to V1. We have a 1. And this is it. Nothing else. 0, 0, 0. So V3 is connected to V2, 1 here. It has a loop, 1 here is connected to V4, 1 here. And finally, V4 is connected to V1 twice. It has no connection to V2. It's connected to V3, and it has no loop. So it's like this. So in this case, since this is a directed graph, where we interpret each non-directed edges as direction both ways. So this in our situation is the same as having 2 edges, one going one way and the other going another. So we're getting such a matrix. It's not a symmetric matrix for a directed graph. But for a non-directed graph, it's a nice symmetric matrix. Okay. Now a very interesting problem, which is mostly solved, but still there are papers about this. If G is undirected, then A of G is a symmetric matrix, yes? We know that symmetric matrices has all real eigenvalues. So what can be said about the eigenvalues of A of G and their connection to graph properties of G. Properties. So this is a nice area of research. It has been done mainly, and there are many hundreds of papers about this, but it's still a nice question. You can try to think yourselves a little bit. Maybe you can discover some basic things. Okay, so I still need some more definitions. a graph, say an unoriented graph, is called connected. Is called connected if there is a path connecting any two vertices of G. Yes. And graph is called disconnected otherwise. So connected graphs with a minimal number of edges. So connected graph on n vertex.
Unoriented.
Yeah. Sorry.
In the beginning, does it say unoriented?
Unoriented, yes.
Okay.
Because for oriented graphs, you should talk about directed paths. So you can also talk about connected oriented graphs, but then you have to be more specific. What do you mean? So apparently, for the most natural thing for directed graphs would be if, I wrote unoriented, I mean undirected. Sometimes that's also the undirected. That's the same thing. So there are usually several words for one and the same notion. So if you talk about directed graphs, you want a good notion of connectedness, then you probably mean that you can go from any vertex to another one using directed edges. You cannot go against the direction. So connected graphs on n vertices with a minimal number of edges are called trees. Okay. So let me illustrate this. So this is connected, and this is not connected, disconnected. So a disconnected graph consists of some bunch of connected components. Yeah. So for example, here you have two connected components. So connected components are its pieces, are its subgraphs, where you can reach any vertex from any other vertex inside the subgraph. So naturally, any undirected graph splits in its connected components. And if it's connected, it's always just one connected component. Okay, so what is, okay, so now I'm asking you, say, if we have 5 vertices, how many edges do we need? What is the minimal number of edges we need to make it into a connected graph? What do you think?
Same as number of vertices?
This would be
no, -1. -1, I'm sorry.
Yes, yes. So we can do it like this, for example. So the minimal number of edges, to make a connected graph is n-1. n-1, yes. And such a connected graph with a minimal with n-1 on n vertices with n-1 edges is called a tree. It looks like a tree in some sense. So okay, how many, so since we're discussing combinatorics, how many trees on n vertices are there? Okay, well, it depends again. If we do not, if we study them up to isomorphism, the answer probably would not be so nice, although it's a much easier question than the question about calculating the isomorphism classes of all possible graphs. Okay, but let us draw, say, for n equals 5. Let's see, let's do it for small n. So 2 vertices, we have just one guy, n equals 2, yes, n equals 3. We still have just one guy, nothing else, n equals 4. Here things start happening. So we have this guy, but we also have this guy. So there are 2 different trees, non-isomorphic. Now n equals 5, what happens then? So we always have a long path, yes, with 4 edges. Then we have then we have a guy like this. Let's see, guy like this, I think, yeah. 1, 2, 3, 4, 5. And then we have like a small bush, yes. So this would be the third one. Now for n equals 6, so we have a long path. Now we have a guy like this. 1, 2, 3, 4, 5, 6. And we have a guy like this. Now 1, 2, we have like this, and finally we have a situation like this. And if you try to draw those pictures with increasing n, you'll easily see that it's not so simple to count those objects, even if those are the simplest possible types of graphs. But if you'll be talking about labeled graphs with labeled vertices, this would be much easier, of course. Okay, let's see. What is it that... maybe we'll make a short break now. Yes, 5 minutes. I guess that's a good point to stop at the moment.
Boris, you're muted.
Boris, you're still muted. Nobody can hear you.
Wow, wow, sorry for that. Oh, sorry for that. Do you hear me now?
Yes, thank you.
Okay, incidence, I forgot how, so sorry for that. So for a given graph G, we create its incidence, I think it's, what's the spelling? Incidence, maybe like this, matrix. So what is this? This is a typical non-square matrix. So its rows are labeled by vertices, and the columns are labeled by edges. And again, if a vertex is adjacent to a given edge, we put a 1 here. So the entry ij equals 1, or maybe some number if we allow multiple edges, but say typically 1 if the vertex vi is 1 of the endpoints for the edge j for ej. So in many applications, the incidence matrix is more convenient, although it looks more clumsier than the adjacency matrix, but sometimes it's easier to work with for several purposes. And for example, if you multiply the incidence matrix by its transpose, which is done in many cases, you are getting another symmetric matrix. And yeah, its spectrum would be interesting. Its set of eigenvalues and how is it related to the properties of the graph is a very interesting property, also fairly well studied, but not completely as studied as about the spectrum of the adjacency matrix. Okay, so what is it that I wanted to tell you now? So here is a very basic, fundamental, still unsolved question. Unsolved basic problem in graph theory. So please solve it. So you'll be famous. So how quick you can recognize if two graphs are isomorphic? So this is a kind of algorithmic question. So say if you have two graphs represented by the adjacency matrices, for example, what is a quick algorithm to understand whether they are isomorphic or not? Well, there is a stupid way to do it, of course, but this is computationally very non-effective. So first of all, for two graphs to be isomorphic, they definitely need to have at least the same number of vertices. So you label vertices of one guy from 1 to n, and you label the vertices of the other guy, say w1 to wn. And you can start matching them in all possible ways. So the number of matchings equals the number of permutations, which is n factorial. And if you match them in some way, you can easily check if edges would be mapped to edges or not. But this, allowing all possible matchings of vertices, requires at least n factorial operations times some checking, additional checking. But the basic difficulty is n factorial. N factorial grows extremely quickly with n. So in practice, it's easy to program an algorithm like this, but it will take you forever to get the result if you work with graphs, I don't know, with 10 vertices already. And 10 vertices is not at all a large number. So there are now practical algorithms solving graph. This is called graph isomorphism problem. So by the way, let me put it graph isomorphism problem. So it's a famous problem. So some people believe that you can solve it in the number of operations you need is a polynomial in the number of edges. Polynomial of some big degree, but a bounded degree. N factorial is not a polynomial. N factorial grows quicker than any possible polynomial in N, yes, when N increases. Some people believe that there might exist a polynomial algorithm. So guess there exists an algorithm to solve it, an algorithm polynomial in the number of vertices, in the number of vertices n. But in general, it's a big open problem, and it's even a practical problem, in fact, because graph isomorphism is applied nowadays in banks transactions and things like that. So there are some practical algorithms doing this quickly for up to maybe something like 30 vertices, maybe 40 nowadays. But still, the general question is interesting and still open, and so on and so on. So you see how basic this thing is. We have spent 1 hour discussing graphs, and I can already formulate a big open question in this area. Okay. Yeah, so let's see. So subgraphs and induced subgraphs. Induced subgraphs. Okay, so given the definition is obvious and natural, so given a graph G, say which consists of a set of vertices and set of edges, we call by its subgraph. So say G prime, which is V prime, and E prime, a graph such that V prime is a subset of V, and E prime is a subset of E with vertices belonging to V prime. Yeah. So here is a basic example. Say if I draw something, I don't know, like this. So, and then from these graphs, so this is my G, and then I can say pick a thing like this. So call it V1, V2, V3, V4, V5, and this would be my subgraph G prime. So I'll be keeping V1, V2, V4, and V5. And I'll be picking edges. So these edges which connect those vertices. But notice here that I just pick some edges, not all edges connecting my chosen vertices. So if E prime consists of all vertices connecting V prime in G, then G prime is called induced. Induced. So an induced subgraph is defined by which vertices of the original graph we have chosen, and then we have to pick all edges in the original graph which use only those vertices. So to get, in my example here, to get the induced subgraph, so the induced subgraph, yeah, if we pick those 4 vertices here, so we should have gotten this guy. So this G double prime is induced. Mhm. So this is the induced subgraph. Yeah, so let's see, how can I mute? Okay. So induced subgraphs, they are in one-to-one correspondence with subsets of just subsets of vertices in the original subgraph. Concerning graph isomorphism, there is a big open question like this. Another open problem in graph theory. So is it true, question, is it true that given G1 and G2 with n vertices, if all induced subgraphs on n-1 vertices in G1 are isomorphic.
Someone has forgotten to mute.
Yes, and I don't quite see who. This is, so I would be happy to unmute. I don't see how to do that.
It's fixed now.
Okay, good. Isomorphic to those of G1. Is it true that then G1 and G2 isomorphic? So we're saying we're given 2 graphs, and say we have a one-to-one correspondence between the vertices, such they have to have the same number of vertices, such that if we are removing vertex V1 from G1 and its correspondent vertex W1 from G2, then we get isomorphic graphs. And then we're doing this for V2 and W2, V3 and W3, and so on. So we have a one-to-one correspondence between vertices such that if we're removing pairs of vertices which are in correspondence to each other from G1 and G2, we get the smaller subgraphs, 2 smaller subgraphs, but they are isomorphic. And this holds for any choice of a vertex in G1 and its correspondent vertex in G2. Is it true that the original G1 and G2 are isomorphic? It looks very plausible, and I think it checked on the computer up to, I don't know, horribly many number of vertices, something like 27 maybe. But the general question is still there, it's still open. Okay, about induced subgraphs, in the induced trees. This is a nice classical piece of graph theory, which was discovered by this German chemist in the late 19th century. I forgot the name, it will come back. Okay, so counting induced trees. So this problem is important in physics, in connection with molecules and the representation of molecules. So given a graph problem, given a graph with labeled vertices, we don't want to switch around vertices. Graph G, how many induced trees does it have? Oh, sorry, it's called, this is called, not induced, I'm sorry, that's a wrong terminology. These are called spanning trees. Spanning trees. Spanning. Spanning trees. Okay, so let me first illustrate this in a particular case, so you'll understand what is it we're talking about. So here is, say, my graph G with vertices V1, V2, V3, V4. And I want to remove its edges in a different way, so such that what will remain after removing of my edges would be a tree. So let us try to draw its spanning trees in this case. So which spanning trees can we get? Say, so let me draw some of them. Hopefully I'll draw all of them. So this would be V1, V2, V3, V4, one guy. So I'll have V1, V2, oops, V1, V2, V3, V4. So 1, 2, 3, 4. Now, what would be the next choice? We can have, so we can have 1. I want to pick 1, 3. 1, 3, 4, and 2. So let's see, I can have 1, 4, this guy, 1, 2, 3, and 4 here. I can have a guy like this, 1, 2, 3, 4. Maybe this is it. I'm not 100% sure. No, I'm not. So no, there is another guy like this at least. 1, 2, 3, 4. Now I'm fairly sure that I counted all of them. So I got 6 different spanning trees coming from my original graph G. So a spanning tree again. So we are removing edges one by one till we get a tree. So we're assuming that our original graph is connected, of course. Otherwise, there are no spanning.
5, not 6.
Huh? 6. No, 6 here. No. Oh, yeah, I think.
No, that's.
So
I count 5. 5 unique.
Yeah, I think I draw this guy in the wrong way. Let's see. I think I meant that thing. So then it's probably, well, we have a square. From square, now I'm still missing one. Let's see. Since we have this square, we can remove so which I'm missing? So this edge. I think I'm still missing this guy. 2, 1, 3, 4. Yes, so this should be still there. Well, anyway, what I want to say, and hopefully now this, no, this is still not it. I'm sorry. So we're still missing this guy. 1, 2, 3, 4. And I don't dare to say that this is it, but I really hope that this 1, 2, 3, 8 guys would be probably the complete answer to my question. What I want to say that there is an excellent theorem by what is his name? It will probably come back. Is as follows: the number of spanning. So given a connected graph G, take its adjacency matrix, A of G. It's called matrix tree theorem. And say remove its first row and column. Its first row and column. It actually doesn't play a role which one, but we have to remove the same row and the same column. So now the resulting matrix is denoted, say, by A tilde G. It's a matrix of size n minus 1, when n is the number of edges. Now, theorem is the number of spanning trees in G equals the determinant of this matrix. Very interesting result. Yeah, so I'll probably provide some illustration for you till next time, and to show, and I can also check if this thing, if we have counted all spanning trees in this particular example. Probably I don't want to do this at the moment, not to lose too much time. Okay, so so this is some other maybe important, basic, fundamental example of, and as I said, this example was this result was discovered by a chemist who wanted actually to study the number of isotopes of certain molecules. So his motivation was quite different, but he discovered an important result in mathematics. Let's see. So maybe two more definitions. Eulerian graphs, and I think, and Hamiltonian graphs. I think we'll be talking about those things next time. I just want to formulate those definitions. So a graph, a connected, undirected graph G is called Eulerian, and this is because the topic I started with Königsberg's with bridges in Königsberg is what resulted in this notion. If there is a closed path in G using all its edges. In other words, you can start at some vertex and go once and use and make a closed path in the graph using all its edges exactly once. So what is a basic example of a thing like this? Say if we have something like I think if we have a complete graph with, okay, so yeah, so let me do this thing. This is an Eulerian graph. This is a complete, oops, I'm missing one edge. I mean, all edges on 5 vertices. So how can we find its Eulerian path or its Eulerian loop? So say we start here. So 1, then we go into here 2, go into here 3, 4, 1, 2, 3, 4, 5. Now going back to 1, 6. I'm going back to here, 7. Or maybe I should label the edges instead. Yeah, so this would be a better idea. Sorry, let me remove those labels. I'll put my labels on edges, so we'll see what we're doing. We start here, so this is number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, and finally we're getting back number 10. So there is a nice, very nice and simple result characterizing Eulerian graphs. And we'll talk about this next time. Now, a similar notions where you're only allowed to visit each vertex once is called a Hamiltonian graph. Again, a connected graph, undirected graph G is called Hamiltonian. Lord Hamilton, he was a Scotch nobleman in the middle of the 19th century who made important contributions to linear algebra, abstract algebra, graph theory, and so on. If there exists a path using all its vertices and passing through each exactly once. So we're not allowed, we are looking for a path now which will connect all vertices, and we're not allowed to use any vertex more than once. Now this question looks quite similar to, this notion looks quite similar to the notion of an Eulerian graph, but it turns out that classification of Hamiltonian graphs, is a much more difficult question. Much more difficult question. So in graph theory, it's sometimes difficult to say. So there are similar notions for edges and for graphs, and one characterization of problem can be very easy one, and another one can be very difficult one. Okay, so I guess maybe this is it for today. Yeah, and yeah, you'll have your seminar session soon enough. So I'll be finishing now and I'll be posting this soon. and we'll continue working with graph theory next time. Okay, good. So I'm stopping, and we see each other on Monday then. Bye bye.
Bye. Thank you.
Bye.